In the last few videos, we've been looking at the molecular geometry and electron geometry for molecules that have 2 through 6 areas of electrons around the central atom. So far, every example that I've used, the areas of electrons around the central atom have only been bonds. We have not yet seen any examples of molecules that have lone pairs on the central atom. And so that's what we're going to work on next. In this video, we're going to be looking at molecules that have 3 through 6 areas of electrons. At least one of those areas of electrons is a lone pair. And we are going to start with 3 areas of electrons. Now what I have here in this column, ALCl3, is information that we already covered in a previous video, and I just have it here for reference. We're going to be working on the nitrite ion, NO2-. As you can see, looking at the central nitrogen atom, if we focus on that nitrogen atom, we can see that we have 3 areas of electrons around the nitrogen. We have a single bond, a double bond, and a lone pair. So 3 areas of electrons around the central atom, 2 of them of those areas are bonds, and 1 area is a lone pair. We want to next think about what the bond angle is for this molecule, and the bond angle is the oxygen to nitrogen to oxygen bond. So what is the angle of this bond? For aluminum trichloride, we said that this particular bond angle was 120 degrees. We call that the ideal bond angle, like the perfect gap that helps keep those bonds as far apart as possible. When we have a molecule like nitrite that has a lone pair of electrons on the central atom, what we do know is that that lone pair of electrons occupies a wider area of space than the electrons in a bond. The electrons in a bond, because they're spread out kind of in a cylindrical shape between those 2 atoms, they occupy a narrow area of space, whereas the lone pair, because it's not being spread out or pulled to another atom, it occupies a much wider area of space. The electrons in this lone pair, because they're occupying such a wide area of space, repel and push down on the electrons in the bond. Again, this is just to keep the negatively charged electrons away from each other, the lone pair and the bonding electrons, just trying to stay as far apart from each other as possible. So again, the lone pair pushes down on these bonds to try to get the bonds away from the lone pair, and this causes these bonds to move slightly closer together. So the angle between the nitrogen and oxygen bonds is something less than 120 degrees, again, because that bond has just been pinched and pushed closer together. We don't know the exact angle of this particular bond. Well, actually we do. If we wanted to get online and look this angle up, we could determine and find exactly what this bond angle is. But the actual bond angle of a molecule that has 2 bonds and 1 lone pair on the central atom depends on the exact atoms that are involved in the molecule. So this particular molecule itself might have, I don't know, a bond angle of, let's say, 119. But if we change these atoms up, the bond angle might be 118. And so just to keep things simple for students, when we're asked to report the bond angle of a molecule like this, we just simply say that it is less than 120 degrees, and we call it good. Let's talk now about the molecular geometry and electron geometry. Now, as a refresher, because it's been a while since we looked at these two, the difference between the two, when we're looking at the electron geometry of a molecule, we are just looking at all areas of electron density. All the areas of electrons. So it doesn't matter if it's bonds or lone pairs. All that we're looking at is what is the total number of areas of electrons. Now the total number of areas of electrons for the nitrite ion is 3, and therefore the electron geometry for the nitrite ion is trigonal planar. Anytime we have 3 areas of electrons, it does not matter if those are bonds or lone pairs or what they might be. Anytime we have 3 areas of electrons, we have a trigonal planar electron geometry. The molecular geometry only looks at the bonds. So we only look at the bonds and we ignore the presence of lone pairs when we're determining the molecular geometry. Let's take a look at this molecule in mole view so we can see what it looks like and that'll help us determine what the molecular geometry is. So I already have this molecule built. If you're new to these videos, if you're jumping in right now, Mole View is a free website that you can use to model these molecules and gives you a chance to get an idea of what they look like 3-dimensionally. So as I'm rotating the nitrite around, you can see that all of the atoms are in the same plane. So this molecule is flat, just like ALCl3 was. And if we look at this particular molecule, all that we can see, we can't see the lone pair of electrons on the nitrogen. They're not being represented. So what we see is the molecular geometry. We see the shape of this molecule. This particular molecular geometry is called bent because it has a bent shape. Some people call it V-shaped because if I flip it upside down, you can see that it looks like a V. If we wanted to draw this molecule three-dimensionally, we really wouldn't have to worry about drawing it three-dimensionally because it already is represented, drawn in a way that represents the shape of the molecule. So there's a three-dimensional drawing. And as far as having three areas of electron density for our trigonal planar electron geometries, this is all that we have. It's all that we have to think about. So let's move on to 4 areas of electron density. Now again here I have the CH2F2 as reference. It's something that we've already looked at. And for our first example, we're going to be looking at NCl3. NCl3 has 1, 2, 3, 4 areas of electron density around the central atom. So we've got 4 areas. And one of those areas of electron density is a lone pair. And we see the exact same situation. Let me make a note here that we have 3 bonds and we have 1 lone pair. The lone pair on this nitrogen has the same sort of effect on the bonds in this molecule as we saw in the last example. Anytime we have a lone pair, that lone pair is always going to be pushing down on our bonds, which is always going to be causing our bonds to shrink up a little bit, and our bond angle is going to be something less than 109.5 degrees. The electron geometry, remember, does not take into consideration whether our areas of electrons are bonds or lone pairs. So whenever we have 4 areas of electrons, regardless of if they are bonds or lone pairs, we always have tetrahedral electron geometry. Let's take a look at what this molecule, how this molecule appears in 3 dimensions. So I am going to change this molecule up a little bit. I'm going to change those oxygens to chlorines, and I'm going to add a 3rd chlorine on there. Let's get a bond to that chlorine. I need to change this bond to a single bond, and I need to get rid of the negative charge on this chlorine. So there is our NCl3 molecule. I don't need to put lone pairs on this in mole view. And here is NCl3 in 3 dimensions. So first I'm going to arrange it so that it matches up with the Lewis structure that we have for the molecule. And now it kind of looks like the AlCl3. It kind of looks like trigonal planar, but I'm going to rotate this. So you can see as I rotate it that this molecule is in fact not flat. It's pretty close to flat, but it's not flat. That if I'm trying to line all 3 of the chlorines up so that the chlorines are all in a line. And if I can do that, you'll see that that nitrogen, the blue nitrogen atom, is sticking up higher than the chlorine. So it's got kind of a buckle to it or a bend to it. So this is not a flat molecule. It does have some shape to it. That nitrogen is just kind of puckered up. This particular molecular geometry is referred to as trigonal pyramidal. It gets its name because its shape is kind of like a pyramid. I mean, it's not a very pointed pyramid. It's kind of a stunted pyramid, but it is pyramid-ish, and the base of this pyramid is a triangle. And so again, it's not a very good pyramid. It's not a high pyramid, but it is pyramidal in its shape. If we wanted to draw this molecule 3-dimensionally, it would be really handy to take a look at how we drew the tetrahedral molecule CH2F2. What we're going to do here is just pretty much mimic that drawing, but we're going to take one of those bonds and eliminate it and just turn it into a lone pair. So this is going to be our 3-dimensional drawing for a tetrahedral molecule that has trigonal pyramidal molecular geometry. Now when we have 4 lone pair or 4 areas of electrons around our central atom, we can have 3 bonds with 1 lone pair, or we can have, in this case, 2 bonds with 2 lone pairs. So 4 areas of electrons, 2 of those areas are bonds, and 2 of those areas are lone pairs. we are still going to see the exact same distortion of our bond due to the presence of the lone pairs. Even though there's 2 of them this time, we know that our bond angle is going to be something less than 109.5. Because we have 4 areas of electron density, our geometry, our electron geometry, is always tetrahedral. Let's remodel in mole view. Let's change this up a little bit. So I've changed the central atom to an oxygen and changed the outer atoms to hydrogen and got rid of one of the outer atoms. And here is our water molecule. Here's what it looks like. Now this is a molecule that, a shape that we actually just saw. Notice now, again, that the atoms have returned to being flat. They're all in the same plane. They're all flat. And we have, again, that same V shape or bent shape. Fortunately, we give this the same name, bent or V-shaped. So we can see that there are 2 possible ways, so far we've come up with 2 possible ways to get the bent or V-shaped arrangement of a molecule. And we have one option, 2 bonds with 2 lone pairs. The other option that we saw was 2 bonds with 1 lone pair. Now let's go ahead and draw this 3-dimensionally. Again, I'm going to use the same strategy that I used previously. I'm just going to eliminate one of the bonds from my previous drawing like that. Now this isn't the only way that you could represent water. I mean, most people, I think I'm kind of overkilling it. Most people are just going to do this because it is just a bent molecule and all the atoms are in the same plane, and that's fine. And so these are all of our 4 areas of electrons with lone pairs on the central atom. Now we're moving on to 5 areas of electrons. Here is the example that we have already seen, phosphorus pentachloride. The first molecule that we're going to look at here is SF4. We can see that there are 5 areas of electrons on that central atom. 4 of those areas are bonds. 1 is a lone pair. And we know that our electron geometry is going to be trigonal bipyramidal. I'm just going to draw an arrow so that we don't have to write all of that back out again. Let's go back to mole view and let's actually model what this looks like, what SF4 looks like. So I'm changing my central atom to sulfur. I'm going to put some fluorines around the outside. I'm going to add a couple more fluorines to the mix and connect them with some bonds. I don't know why it just changed my central atom, but we can change it back, and let's go ahead and model this. Now, this is actually one that mole view, I just immediately dismissed that message, but this is actually the only one that we're going to see in this video that mole view does not accurately model. Mole view makes it look like this, takes a shape you've seen before. This is called the tetrahedral shape, and this is actually an inaccurate shape for this particular molecule. What I'm going to do is attempt to draw it over here in this space, and hopefully you can visualize what it would look like. So when this molecule, when we put a lone pair on this particular molecule, the lone pair chooses to place itself in any one of these 3 positions that I just circled in red. So for the sake of this drawing, I'm going to put the lone pair right here, and then I'm going to have my fluorines like that. And so this is actually the shape, it's, like I said, not being accurately represented in mole view. In the actual molecule, this bond, the fluorine to sulfur to fluorine bond, is a linear bond, and this is 120 degrees off to the side. So for this particular molecule, we do still have the 90-degree bond angle, which is what we see right here. That one has not changed. This bond angle right here, with the presence of the lone pair, is being kind of pinched down. So we do get a less than 120-degree bond angle in that particular spot. This molecule's name is called seesaw. Seesaw is another word for teeter-totter. If you don't know what either one of those things are, I'm going to try to rotate this. So this is a toy that is found, it's like a piece of playground equipment. This is a log. It's got a seat here and a seat here. It's kind of like legs on a platform right here. Kids can sit on the seesaw and they just tip it to one side and then tip it to the other, tip it back and forth. And because of this particular shape, it gets that name seesaw. And so that's sort of the history, I guess, of where this name came from. And again, Molview falls short in representing this particular molecule. It just shows it as if it is tetrahedral. But Molview does not make any mistakes on any of the rest of the ones, so let's move on to our next example. In this one, we have five areas of electrons. 3 of them are bonds and 2 of them are lone pairs. And let's go ahead and take a look at what that molecule looks like. So we want iodine on our central atom, and we want only 3 fluorines on the outside, so I'm going to delete one of them, and then we'll go ahead and model this. And here is what this one looks like. So you can see that we've got, if we go back to looking at this diagram right here, but now we have an iodine in the middle. We still have the fluorine, iodine, fluorine, which I'm putting up nice and straight in a row. And then all that we've done is taken one of these fluorines, either one of them, and turned that into a lone pair. So this is the shape that we end up getting. Now, there are some lone pairs on this particular molecule, but they don't really cause any sort of distortion to the bond angles. The bond angles are exactly what we see, which is 90 degrees. Now, there is, if I turn this way, there is a 180-degree bond angle as well, but we usually don't talk about that. We just talk about the 90-degree bond angle that we're looking at right there. And this particular molecule's shape is T-shaped, with trigonal pyramidal electron geometry. If we wanted to draw this three-dimensionally, we would just simply draw exactly what we see in Molview. I've got it rotated a little bit, but this is what the T-shaped molecule looks like. And we are now ready to look at our last example of the trigonal bipyramidal molecule. This one is 5 areas of electrons. 2 of them are bonds. 3 of them are lone pairs. Let's go ahead and convert this into our last molecule. So this we have I3-. We've got to delete one of these fluorines. And in order to make this molecule work, I've got to put a negative charge on our central iodine. And then let's take a look at what we get. There it is. Not only is it pretty purple, but look at that shape. So we've got all 3 of those iodine atoms, and notice that they are all in a perfect line. We've seen that shape before. We've seen that bond angle before. That's 180 degrees. Whenever we have those atoms all in a line, we call it linear. And in terms of drawing this molecule, we're just going to draw it in a way that shows the nice linear shape. Make sure that we get all of the lone pairs, and don't forget the negative charge. Now we're almost done. Hang in there. We're on to 6 areas of electron density, and this is what we have seen so far. For our first example, we have 6 areas of electron density. 5 of them are bonds, and 1 is a lone pair. And the electron geometry is going to be octahedral because, again, electron geometry only depends on the total number of areas of electrons. It doesn't matter if they're bonds or if they are lone pairs. Let's build this molecule. So for this molecule, I'm going to need to put a few more outer atoms. Let's see, we have 5 fluorines, so let's get those all connected together. And I need to change the inner atom to a xenon. And I'm going to need to put a charge on that xenon atom. There we go. And let's see what it looks like. So here it is. Look at that. So first thing we're just looking at are the bond angles. Now recognizing that we do have a lone pair on the xenon, which means that we are going to be seeing some pushing down of our bonds. If I rotate this right now, you can see that there's a 90-degree bond angle in this molecule, but if you envision that lone pair that's sitting on top of the blue sphere, it's going to be pushing down on these xenon fluorine bonds, and that is going to cause that 90-degree bond angle to shrink a little bit. So our bond angle is going to be something less than 90 degrees. The molecular geometry, the name of the molecular geometry comes from viewing the molecule from this perspective, and we can see that it is, again, it's kind of a pyramidal shape if you imagine connecting the fluorines to each other. This pyramid has a square-shaped base, so we call this molecular geometry square pyramidal. And if we wanted to draw this three-dimensionally, we would take this particular model and just simply remove one of the atoms, one of the bonds, and turn it into a lone pair. Let's draw it from this perspective right here. So we're going to put our xenon, we're going to have one fluorine sticking up, and we'll have our 4 fluorines sticking to the left and to the right, with a lone pair down on the bottom, and all of the lone pairs on the outer fluorines. And then we also have the overall charge. So we've got to put this in square brackets. Overall charge. We have one more to go. So here is our last one. Very simple, similar molecule. 6 areas of electrons, 4 bonds, 2 lone pairs on the central atom. Again, the electron geometry for this is going to be octahedral. Let's change our mole view drawing. We've got to get rid of one of the bonds, and we also have to get rid of that charge on the xenon. It's not charged anymore. Let's see what this looks like. If we turn it, we can see that we have all of the atoms in the same plane. So this is flattened out, completely flattened out. The bond angle here, this is an interesting thing to think about. We do have the lone pair of electrons. If I hold it like this, you can imagine there's a lone pair of electrons on top and a lone pair of electrons on the bottom. So we've got the lone pairs are sitting on the xenon, and one of them is going to be sticking up, and that one that's up on top is going to be pushing down on the bonds. And then we also have a lone pair on the bottom side of the molecule that's pushing up on the bonds. So we have one pair pushing down, and we have another pair pushing up, and it works out to be a tie. And in this particular molecule, there's no distortion on the bond angle at all. It just returns back to a perfect 90 degrees. This shape, because it's flat and it's square, is called square planar. And the easiest way for us to draw this shape is to just simply draw it like looking at it from this perspective. And that's not a fluorine, it's a chlorine. Draw it like this. Now you have made it through all of these molecules, and you have a summary of every possible combination of bonds and lone pairs on the central atom.